If we have this picture, then we need to make the bias sources. And making the bias sources, designing them themselves is not the topic for today. Today, we want to stick to this concept and we'd like you to work it out for the antenna amplifier, for the active antenna. But of course, we need to specify the sources and you can just say, for the rest, it's the same as building an amplifier. We have to set up specification for the sources and build a reference, a current or voltage thing. So if we build a current source, we must relate the current to the power supply voltage and build some kind of voltage to current converter, which is a transmittance stage that has sufficiently high output impedance and a low noise. That's basically what we are going to do. So we just derive the specifications from the amplifier specifications. And there are a lot of relevant amplifier specifications involved. Of course, the noise, the drive capability, the power consumption, the power supply reaction ratio. That has to do probably with the impedances that we are inserting there. The common mode reaction ratio in case, and this is not in the picture that I've shown, in case that we have a floating input or output port, and the gain inaccuracy, uh, uh, and the weak nonlinearity and the temperature dependency. And I did not mention the offset itself at the input, so that is the accuracy of the biasing itself. I just included it more or less in the temperature dependency. All those parameters depend on temperature. As you can say, every meter is a thermometer. That's physics. So the bias voltage sources, we have to specify from the voltage sources the voltage, the total error. Oh, there's some flashing thing for later. The total error, the saturation current, as we have seen from this picture, the cutoff current, as we have seen from the picture, the small signal impedance, the noise spectral density. That is all what we need to specify from the voltage sources. And let's say we can already do a lot of this work. And of course, we need to do it before we are going to design the bias sources themselves, but we can do it in the small signal equivalent diagram. If we know where the voltage source will be, we can insert an impedance in the signal path and find a budget for it so that its contribution, for example, to noise or to the high frequency behavior is, let's say, it is not deteriorating the behavior. That is what we can do. And for current sources, of course, we need exactly the same. We need to know the current, the total error for it relates to the offset we get at the input. And then we have the saturation voltage, the breakdown voltage, the small signal impedance, and the noise. And also here, let's say if in our antenna amplifier, we are going to implement a bias source, we can already in the small signal diagram insert, for example, a parallel connection of a resistor and a capacitor, because we know that most transistors that we are going to use have a output impedance, basically if you don't do any feedback around them, like a resistor in parallel with a capacitor. That is what we have seen many lectures ago when we discussed the CS stage. So then we can get a budget for the impedance that we are going to insert in the signal path. And we can also find a budget for the noise. We know if this is, for example, a current source biasing the input stage, that any noise provided by that current source will be in parallel with the input stage noise itself. It will just simply add. So the rule is it must be much smaller than the noise of the first transistor itself. And in this way, we can find requirements and see before we are going to dive into detail if things are feasible. That is always the aim of structured design, that we first put our considerations and look in the circuit and say, are we not going to run into showstoppers if we dive into the detail? Because the details work is a lot of work, a lot of simulation for verification at the end, because that's what we need to do. At the end, we are going to check the performance and then um, do improvements if necessary. But before you check the performance, and the more experience you have, the more you can do that, you can already try to find an estimate. Like say, can I make this current source with less noise than is already there? And if not, then we have to go to another concept for the signal path that is easier to bias, find something else. So that is the way it works. Don't dive into detail if you can already see something at an earlier level. That's very important.